are generative adversarial networks, GANs, truly ushering in an era of machine creativity, or are they merely sophisticated tools of digital deception? This question strikes at the heart of modern artificial intelligence, challenging our understanding of artistic expression and algorithmic innovation. Imagine machines capable of generating original art, music, and even literature, blurring the lines between human ingenuity and artificial mimicry. Delve into the fascinating world of GANs to explore if these networks are creating genuine creative breakthroughs or just masterful illusions of creativity. Generative Adversarial Networks, GANs, are a class of machine learning models that have emerged as a groundbreaking force in artificial intelligence, capable of generating remarkably realistic data. Their significance lies in their ability to learn the underlying patterns of a dataset and then create new data that mirrors this learned distribution, enabling applications from image synthesis to drug discovery. Unlike traditional discriminative models that classify data, GANs are generative models, meaning they create new instances rather than just categorizing existing ones. This generative capability opens up unprecedented possibilities, making GANs a pivotal area of research and development in AI with the potential to revolutionize various industries. Generative Adversarial Networks, GANs, are aptly named for their innovative structure, which pits two neural networks against each other in an adversarial game. The term generative highlights their primary function: to generate new data instances that resemble a given dataset, unlike models that merely analyze or classify data. These networks are adversarial because they involve a competitive process between two key components striving to outdo each other, leading to continuous improvement in data generation quality. Think of GANs as digital artists and critics locked in a perpetual loop, pushing each other to refine the art of data creation. A generative adversarial network, GAN, fundamentally consists of two neural networks, the generator and the discriminator, each with distinct yet complementary roles. The generator functions as a creative forger, tasked with producing synthetic data samples intended to mimic real data, much like an artist creates a painting. Conversely, the discriminator acts as a critical judge, scrutinizing both real and generated data to distinguish between the authentic and the artificial, similar to an art expert evaluating a painting's authenticity. This duality of roles is crucial, as the interplay between these two components drives the learning and data generation process within GANs. The training process of a GAN is ingeniously designed as an adversarial competition between the generator and the discriminator, a dynamic described by game theory concept of a zero-sum game. The generator continuously strives to produce increasingly realistic synthetic data to fool the discriminator, akin to a counterfeiter refining their technique to create flawless forgeries. Simultaneously, the discriminator relentlessly learns to become more adept at distinguishing real data from generated fakes, evolving into an ever more discerning critic. This competitive dynamic is essential, as it forces both networks to improve iteratively, pushing the GAN towards generating exceptionally realistic and high-quality data. Compared to other machine learning models, generative adversarial networks, GANs, offer a unique advantage in their ability to generate entirely new content, rather than just analyzing or classifying existing data. While models like convolutional neural networks, CNNs, excel at image recognition, GANs can create original images, surpassing the capabilities of many traditional algorithms that are limited to pattern detection. For example, Markov models and recurrent neural networks, RNNs, can generate sequences, but GANs achieve a higher level of realism and complexity in outputs like images and videos. This generative prowess sets GANs apart, making them invaluable for applications requiring the creation of novel and realistic data instances across diverse domains. The working process of GANs is a fascinating interplay between two neural networks striving for dominance in a data generation game. Initially, the generator creates random data that is easily distinguishable from real data, like a novice artist's crude sketch. This generated data, along with real data samples, is then fed to the discriminator, which learns to differentiate between the two, becoming a more astute critic over time. Through repeated rounds of generation and discrimination, both networks refine their skills, with the generator becoming adept at creating increasingly realistic data and the discriminator becoming ever more discerning in its evaluations, leading to continuous improvement in the quality of generated content. The generator's role within a GAN is to function as a digital artist, creating artificial data from random noise, with the goal of mimicking real data distributions. It employs neural network layers to transform this noise into structured outputs like images, text, or audio, essentially hallucinating data that resembles the training dataset. As training progresses, the generator learns to refine its creations, moving from generating pure noise to producing increasingly coherent and realistic samples designed to deceive the discriminator. Imagine the generator as a student artist, initially producing crude sketches but gradually mastering techniques to create works indistinguishable from a master's originals. The discriminator's role in a GAN is analogous to that of a vigilant detective, tasked with distinguishing between genuine real-world data and fake data produced by the generator. This neural network is trained on both real and generated data, learning to identify subtle features and patterns that differentiate the authentic from the artificial, much like a forensic expert analyzes evidence. The discriminator outputs a probability score, indicating its confidence level that a given input is real. Ideally, it should accurately classify real data as real and generated data as fake. This evaluative function is crucial feedback for the generator, guiding its efforts to create more convincing synthetic data. GAN interaction is the heart of their learning process, representing a dynamic feedback loop between the generator and discriminator designed to optimize data generation. The discriminator's evaluation acts as a crucial signal, informing the generator about the weaknesses in its generated data, pushing it to refine its techniques and produce more realistic outputs. Conversely, the generator's improvements challenge the discriminator to become more discerning, driving it to identify ever more subtle differences between real and fake data. This iterative process of challenge and response, akin to an evolutionary arms race, is what enables GANs to learn complex data distributions and generate increasingly high-quality and realistic synthetic data over time. Loss functions are critical mathematical tools in generative adversarial networks, GANs, acting as the compass that guides the training process by quantifying the disparity between generated data and real data. These functions essentially measure how well the generator is fooling the discriminator, and conversely, how effectively the discriminator is identifying fakes. Two prominent examples are binary cross-entropy loss used in original GANs and Wasserstein loss in WANs, each designed to provide a nuanced metric for evaluating the quality of generated samples. By minimizing the loss function, GANs iteratively refine their parameters, leading to increasingly realistic and higher quality synthetic data generation, pushing the boundaries of artificial creativity. Despite their remarkable capabilities, generative adversarial networks, GANs, are notoriously challenging to train, presenting several significant obstacles that researchers are continually striving to overcome. Issues such as mode collapse, where the generator produces a limited variety of samples, and training instability, characterized by oscillations and divergence, can severely hinder GN performance. Optimizations like batch normalization, gradient penalty, and architectural innovations are crucial for mitigating these challenges, ensuring GNs can learn complex data distributions effectively. The quest to enhance GN stability and diversity remains a central focus, driving innovation in algorithmic design and computational techniques within the field of deep learning. Mode collapse is a notorious pitfall in GN training, where the generator gets stuck producing only a limited set of similar samples, failing to capture the full diversity of the real data distribution. Imagine a digital artist who, after initial success with a particular style, becomes unable to create anything different, endlessly replicating the same artwork. This occurs because the generator finds a sweet spot that consistently fools the discriminator, neglecting to explore other modes or variations present in the training data, leading to a lack of diversity in the generated output. Consequently, mode collapse undermines the GN's ability to generate truly creative and varied content, hindering its potential in diverse applications. To improve the training stability of GNs, several ingenious techniques have been developed focusing on refining both the architecture and the training process. Batch normalization, for example, stabilizes learning by normalizing the input of each layer, reducing internal covariate shift and accelerating convergence. Gradient penalty is another powerful method, especially in Wasserstein GNs, WANs, which enforces the Lipschitz constraint, preventing the discriminator from becoming too confident too quickly and ensuring smoother gradients. Techniques like spectral normalization further control the Lipschitz constant of the discriminator, promoting more stable and reliable training dynamics. These stability techniques are crucial for enabling GNs to learn effectively and generate high-quality, diverse outputs, pushing the boundaries of AI-driven creativity. GN variants, such as Wasserstein GNs, WANs, represent significant advancements designed to address specific limitations of traditional GNs, particularly the problem of training instability. WANs utilize the Wasserstein loss function, also known as Earth mover's distance, which provides a more stable and informative gradient for training, mitigating issues like vanishing gradients and mode collapse common in original GN formulations. Another notable variant, deep convolutional GNs, GANs, incorporates architectural guidelines for convolutional neural networks, CNNs, within GNs, leading to more stable training and higher quality image generation. These GN variants showcase the ongoing evolution and refinement within the field, each iteration bringing us closer to harnessing the full creative potential of adversarial networks. Prompt-based GNs represent a revolutionary evolution in generative modeling, shifting from unconditional generation to highly controlled and conditional content creation guided by textual prompts. Unlike traditional GNs that generate outputs based solely on learned data distribution, prompt-based GNs allow users to steer the generation process using natural language descriptions, offering unprecedented creative control. This paradigm shift enables the creation of specific and customized content. Imagine instructing an AI to paint a sunset over a futuristic city and witnessing the network bring that precise vision to life. This innovative approach opens up vast new possibilities for artistic expression, design, and various creative applications, making AI creativity more accessible and user-driven. To control a GN using a prompt means to guide the generator to create specific types of content by providing textual instructions rather than relying solely on the network's unsupervised learning. A prompt acts as a natural language directive, telling the GN what kind of image, text, or audio to generate, much like an art director instructing a human artist. This control is achieved by feeding the prompt into the GN's architecture, influencing the generator to tailor its output to match the described specifications, effectively transforming the GAN into a controllable creative tool. This level of user-driven guidance is a hallmark of prompt-based GANs, enabling precise and customized content generation. The core difference between traditional GANs and prompt-based GANs lies in the mechanism of content generation control. Traditional GANs operate largely autonomously, learning from data and generating outputs with limited steerability, whereas prompt-based GANs are explicitly designed to be controlled via textual prompts. Traditional GANs excel at learning and replicating the style of a dataset, but lack precise control over the specifics of each generated instance, leading to a degree of randomness in output. In contrast, prompt-based GANs offer fine-grained control, allowing users to dictate the content by providing descriptive prompts that guide the generation process toward desired characteristics and themes. This shift towards prompt-based control marks a significant leap in making AI creativity more directed and applicable to specific user needs and artistic visions. A prompt is used as input to control a GAN by encoding textual descriptions into a format the network can understand and utilize to guide its generation process. Typically, text embeddings, generated by models like BERT or CLIP, convert the prompt text into a high-dimensional vector representation that captures the semantic meaning of the instruction. This embedding vector is then fed into the generator network, often integrated into its initial layers or through attention mechanisms, influencing the data generation at each step. By modulating the generator's input with prompt embeddings, users can effectively steer the GAN to produce content that aligns with the textual description, transforming abstract instructions into concrete and visually rich outputs, showcasing the power of text-guided AI creativity. Prompt-based GANs function by meticulously interpreting textual prompts and translating them into actionable instructions for the generator network. This process begins with prompt interpretation, where a text encoder like CLIP or BERT converts the input prompt into a meaningful embedding vector, capturing semantic nuances and details. These embeddings are then integrated into the GAN architecture, often through architectural extensions like attention layers, which allow the generator to selectively focus on relevant parts of the prompt during content creation. The discriminator's role is also adapted to evaluate not only the realism of the generated content, but also its alignment with the provided prompt, ensuring the output is both high quality and semantically consistent with the user's textual directive, orchestrating a complex yet elegant mechanism of prompt-driven content generation. Prompt interpretation in generative adversarial networks, GANs, is the crucial process where the generator deciphers textual instructions to guide the creation of specific data or content. The generator uses sophisticated techniques, like attention mechanisms, to focus on relevant parts of the prompt, allowing it to understand the nuanced meaning and intent behind the user's request, much like a skilled artist understands a client's brief. For instance, if a prompt requests a photorealistic cat wearing a hat, the generator identifies keywords and visual attributes to tailor its data generation, producing an image that aligns with the detailed textual description. This intricate interpretation mechanism enables prompt-based GANs to generate highly customized and contextually relevant outputs, bridging the gap between natural language instructions and artificial content creation. Architectural extensions are essential for prompt-based GANs to effectively process and integrate textual prompts into the data generation process. Conditional GANs, CGANs, are a foundational extension, incorporating prompt embeddings into both the generator and discriminator networks, allowing them to jointly consider the condition, prompt, and the generated output. Techniques like cross-attention layers and transformer networks further enhance prompt processing by enabling the generator to dynamically focus on different parts of the prompt during various stages of content creation. These architectural modifications are crucial because they provide the necessary pathways for textual information to effectively guide and shape the generative process, transforming standard GANs into powerful prompt-responsive creative tools. The discriminator's role in prompt-based GANs is expanded to ensure not only the realism of generated outputs, but also their fidelity and relevance to the guiding prompts. Beyond distinguishing real from fake data, the discriminator must also evaluate whether the generated content accurately reflects the semantic meaning and details specified in the prompt, acting as a contextual judge. For example, if the prompt is a blue bird flying over a lake, the discriminator checks if the generated image indeed contains a blue bird and a lake, and if their relationship is accurately depicted. This dual role of assessing realism and prompt alignment is critical, ensuring that prompt-based GANs produce outputs that are both high quality and truly responsive to user instructions, achieving prompt-guided creative generation. Challenges in prompt-based GANs arise from the inherent complexity of translating natural language prompts into precise and controllable data generation processes, requiring sophisticated optimizations to overcome these hurdles. One major challenge is ambiguity in prompts, where vague or multifaceted instructions can lead to misinterpretations by the generator, resulting in outputs that don't fully align with user intent. Another significant hurdle is ensuring semantic consistency and contextual relevance, making sure the generated content is not just visually appealing, but also meaningfully coherent with the prompt's implied context. Optimizations in network architecture, loss functions, and training strategies are continuously being developed to address these challenges, pushing the boundaries of what prompt-controlled AI creativity can achieve. Prompt challenges specifically emerge from the nuances of natural language, which can introduce ambiguities and complexities when controlling a GAN. Vague prompts like "create something beautiful" offer insufficient direction, leading to unpredictable and often undesirable outputs, as "beautiful" is subjective and lacks specific, actionable instructions. Conversely, overly complex or contradictory prompts can confuse the generator, resulting in incoherent or erroneous content, much like asking a human artist to paint a sadly joyful scene. Furthermore, ensuring the prompt's intent is accurately captured and translated into visual or auditory elements requires advanced semantic understanding, a capability that remains a frontier in artificial intelligence, highlighting the delicate balance between human instruction and machine interpretation. To ensure that generated results precisely match the given prompt, prompt-based GANs employ several sophisticated techniques focusing on enhanced semantic alignment and contextual understanding. Attention mechanisms within the generator architecture allow it to dynamically focus on the most relevant parts of the prompt during different stages of content generation, ensuring adherence to key instructions. Contrastive learning objectives are also utilized, training the model to maximize similarity between prompt embeddings and generated output embeddings, enforcing a tight coupling between textual directive and visual outcome. For instance, in text-to-image synthesis, these methods ensure that if a prompt specifies a red apple, the generated image unequivocally features a red apple, demonstrating precise, prompt adherence and realizing truly instruction-following AI. Error prevention in prompt-based GANs hinges on strategies that enhance the generator's robustness to interpret prompts accurately and consistently, minimizing misunderstandings. Employing clear and unambiguous prompts is a primary error prevention tactic. For example, instead of "draw a bird," using "draw a bluebird in a pine tree" provides more precise direction. Data augmentation techniques that expose the model to variations of prompts during training help improve its generalization and ability to handle diverse phrasing and sentence structures, much like exposing a language learner to varied dialects. Moreover, feedback mechanisms, where a discriminator is explicitly trained to penalize deviations from prompt specifications, reinforce accurate prompt interpretation, ensuring the GN remains faithful to the user's intended creative direction, refining the art of error-free AI instruction following. Applications and future perspectives for GANs and prompt-based GNs are expanding rapidly, heralding a new era of AI-driven creativity and innovation across diverse sectors. From generating photorealistic images and videos for entertainment and advertising to creating synthetic data for medical research and drug discovery, GNs are proving to be versatile tools with transformative potential. Prompt-based GNs further amplify these applications by enabling user-guided content creation, opening doors to personalized art, customized product design, and interactive storytelling, pushing the boundaries of human-computer creative collaboration. The future promises even more sophisticated and ethically considered uses, with GNs potentially revolutionizing industries from art and media to healthcare and scientific research, painting a vibrant picture of AI's creative future. Practical use cases for traditional and prompt-based GNs are increasingly diverse, showcasing their versatility in manipulating and creating data across various modalities. Text-to-image generation, exemplified by models like DALL-E and Midjourney, allows users to create stunningly detailed images from simple text prompts, revolutionizing digital art and design workflows. In fashion, GNs are used to design new clothing and texture patterns, accelerating the creative process and personalizing consumer experiences. For example, Nike used GNs to design Air Max 1 shoes. Furthermore, GNs are invaluable in medical imaging for generating synthetic MRI and CT scans, aiding in disease detection and research, demonstrating the broad impact of GNs from artistic creation to critical healthcare advancements. Technological advancements poised to further enhance the efficiency and precision of prompt-based GNs are continuously emerging, promising to unlock even greater creative potential. Innovations in transformer architectures and attention mechanisms are leading to more nuanced and context-aware prompt interpretation, allowing GNs to understand and execute complex instructions with greater fidelity. Improved training methodologies, such as contrastive learning and reinforcement learning, are making GN training more stable and efficient, reducing computational costs and development time. Furthermore, research into multimodal GNs, capable of integrating and generating content across different data types, text, image, audio, is expanding the creative scope, paving the way for truly integrated AI creative systems and realizing the full spectrum of prompt-driven generation possibilities. Prompt-based GNs are not confined to solo brilliance. Their true potential may explode when synergized with other AI technologies like large language models, LLMs. Imagine LLMs crafting elaborately detailed and context-rich textual prompts that guide GNs to generate visuals, effectively creating a sophisticated AI creative pipeline. This fusion could lead to revolutionary applications, such as AI systems capable of producing entire interactive narratives or personalized educational content dynamically tailored and visualized from complex, evolving prompts. Astonishingly, this integration could even enable the creation of AI co-authored films, where algorithms not only write scripts, but also generate the cinematic visuals, blurring the lines between human and artificial creativity in unprecedented ways.